Okay, hello everyone. It is 2 o'clock, Friday, the 23rd of April, and we are uh, finishing up today all things hypothesis testing. Now, what I'm going to share today is the P method. Remember, I told you be reasonable, do it my way, right? And that still applies. Right? On Monday, you guys are going to take a test on everything hypothesis testing. And on Monday, I expect that you will do the problems my way. Okay? The reason I'm asking you to do them my way is twofold, right? One is the probability of you getting a good grade goes up exponentially, because the probability of making a stupid mistake goes down quite dramatically if you are reasonable and you do it my methodology way, the 11-step process, right? Okay. Now, what I'm going to talk about today is the P method of doing this, all right? The reason that I'm talking about the P method is it may very well be that people working underneath you down the road who have learned statistics from a different book, or actually your book goes through the P method more than I'd like it to, right? May have learned how to do hypothesis tests this way. And if you understand what they are doing, right, you will be able to look at their work that they present to you and know whether A, it was done correctly, or B, whether they're full of crap, right? Okay. And if they are full of crap, you should know about it, right? And you should also be extremely careful about letting them do stats work for you in the future, right? Now, I am faced with a bunch of folks yearly whenever we do hiring at our university, right? One of the things that we have them, the prospective teachers, do is to teach a class live when it ever is possible, or with faculty members in attendance if students are not on campus at that point in time, right? The other thing we have them do is present their research. And I would say 70% of the time, 75% of the time, their research requires some kind of hypothesis tests regarding whatever they are trying to prove is correct, right? And without mentioning names in any way, because even if we mention names, you probably wouldn't know them, right? I would say roughly half of the people who present their statistics to us, including hypothesis tests in their research, quite honestly, don't know what the hell they're presenting, right? And usually those people are presenting using the P method, right? And you ask them a quick question about their research and their methodology, and it all falls apart really, really fast. And you know, these guys are just, well, I found some formula in the book and I plugged in the numbers where I thought they should go, and this is what I think it tells me, right? And many of those potential faculty members are not teaching at Texas A&M Kingsville. They are maybe teaching at some other university. Bear with me 1 second. I have to get a glass of water because I got a thing in my throat here. So just bear with me 1 second. I just got to get a glass of
Professor, you're muted.
Thank you for pointing out that I was muted. I could have gone on for hours if you hadn't mentioned that. Okay. What we're going to do is I'm going to quickly walk through the 11 method process again, right? And then I'm going to show you how the P method is different, how it tries to shortcut some things. Now, it doesn't completely shortcut it. In my opinion, makes it even harder, okay? But the people who do it, you'll know what it is. The other reason that I'm doing this is on Monday, we are going to talk about regression analysis. And when we do regression analysis, the output that you get from the computer has that P number on it, right? And so that becomes useful to know because it'll help you understand regression analysis. All right, let's walk about how the process, my process, one that you would do because you're a reasonable person, functioned, right? Step number one was we identified it was a hypothesis test question. Same is true from the P method, right? We had to come up with a null hypothesis and the alternative hypothesis. Again, true. P method. Determining whether it's one-sided or two-sided. Okay. Using my method, we need to know that, and it forces you to think about it because you need to shade the areas. So what do I do in my method? We draw two charts, right? The first one is the one that comes from the sample. You know, this is distribution of the sample that we would expect if the null hypothesis is true, right? Then what we do is we ask the question, is it one or two-tailed? If it's two-tailed, we will have two rejection regions. If it's one-tailed, we have to figure out which one it is, right? Let's just say it's one-tailed and the rejection region is on this side. And we draw it and we put alpha is the percent, right? So alpha equals 5%, okay, is kind of the norm. But alpha can be anywhere from, 0.1% to whatever you want it to be, right? This is a decision variable. How often are you willing to tell somebody is a liar when in fact he wasn't lying, right? Are you willing to falsely accuse somebody 1 out of 20 times? If the answer is yeah, 1 out of 20 is not bad, right? That's a 5% rejection region, right? If you want to be extremely careful, if the guy is going to fire you if you ever accuse him of being wrong and it turns out he wasn't wrong, right? If your livelihood is on stake, you say, I'm not willing to make that mistake 1 out of 20 times. There are 20 working days in most months. I wouldn't last here more than a month on average, right? I am going to have alpha be 1%. I'm willing 1 out of 100 times, okay, to call my boss a liar when he wasn't a liar. Okay, he'll forgive me 1 out of 100 times. He's not going to forgive me 5% of the time. In that case, your alpha is 1. Regardless of your methods, you have to pick the alpha-ish. You have to pick the alpha, right? What did my method do? My method drew underneath here the curve that is in your book. The one that's centered around 0, sigma equals 1, right? This is the one, it is either a T or a Z, depending on how big n is, right? and whether sigma is known or not, right? And then what we will do is ask the question, what cutoff value has 5% in the tail, right? And from our tables, we calculate what that is. If it's a Z, it's a 1.645. Okay. Don't believe me, go to the last line on the Z table, right? Z equals 1.645. 1.645. And then when we're all done with this, we calculate the Z test statistic. And what the Z test statistic will tell us, okay, and x bar minus mu over sigma square root of n. It's the first of the 4 different versions, right? We calculate Z test, and then from this Z test, we will look to see where it is. If we get a 1.8 out of here, we go and say 1.8 is larger than 1.645. It is in the rejection region, and hence we reject the null hypothesis. If our test statistic was a 0.327, we go in here, 0.327 is somewhere in here, which is what? In the unshaded acceptance region, right? If we get a number that is a minus anything, a minus 7.2, you go and say a minus is on this side. Well, the entire side of this side is in the unshaded area, and so we are in the acceptance. Remember, the unshaded area is the acceptance region. The shaded area here is the rejection region. Okay? Now, we can set everything up. We can set the entire test up before we go get that X bar. And when we get the final results from X bar from our sample, all we have to do is plug it into this formula, which can be pre-populated with all the other numbers we need, right? Right? Well, we will plug in X bar and we'll plug in S if we need it, right? Okay. Sigma is given to us. We don't need to estimate what God has already told us, right? So our method uses this Z-test number and just goes and says, physically, is it in the shaded area? It's in the shaded area. We reject the null hypothesis because this is the rejection region, right? If it is in the unshaded area, it is in the acceptance region. So all we do is, once we have computed that, go and see where it falls on the x-axis. Does it fall down here where it's unshaded, over here where it's unshaded, or in the shaded area? And we make our rejection statement. Okay. So how does the P method differ? Well, in the P method, it says we don't have to draw this chart. Okay. As a matter of fact, most people who do the P method don't even draw this chart. although they should. Let's assume they did draw that chart. So what does the P method do? The P method takes this z-test number and they look this one up in the z-table or in the t-table. Now, there's a couple different things. In the z-table, it works relatively easily, right? If this comes out to 1.36, 1.36, right? If our test statistic happens to be 1.36, we will look this up in the normal table, the normal z-table, as 1.36, right? And what the normal table will tell us, what we want to know is on a standard normal in the back of the book, when we look this up, and I'm just going to do it right now. Okay, I am going to, I hope I have a normal table. I think so, out there. Share application screen, share entire screen. Okay, you guys should be seeing my screen. And I'm going to quickly see if I can. No outputs found there. Okay, I'm pretty sure I have one on the home page. I know I have T tables out here. I'm pretty sure I have the Z table as well. Normal table. Right? Okay. 1.36, I want to look that up. And remember, this is the table here, right? Now, looking at 1.36, 1.36 is 1.30, 1.31, 1.32, 34, 35, 35, 36. And 1.36, I have 0.9131. 0.91. Okay. Stop sharing. You guys see where I got 1.36 being 0.9131? But remember, look up at the shaded area. What does that point? What does that 0.9131 represent? It represents the shaded area from minus infinity until this 1.36 number, the z-test number, right? Was that the part that's interesting to us? No, the part that was interesting to us is the tail. What is the probability of being in the tail? Well, it's 1 minus what is on the chart. So here is a problem that many of you will make when you use the P method, is you will calculate the P method for calculating the P that corresponds to the z-test number, and you are potentially going to get the opposite of what you need if you forgot that this chart doesn't show you the shaded area in the tail. It shows you the area that's not shaded in my chart, right? Furthermore, when you use the t-tables are not really set up to do it in this direction. So it is very difficult to get a p-value from a t-table. They're just not set up for it, which will get you a big problem if you use the p method. Okay. All right. So what have we done? Let me go back. You guys should be seeing me again. Is that correct? Can somebody just verbally say, yes, we see you?
Yes.
Okay, great. Okay. So when we look up the p-value of 1.36, it is taking the z-value here, looking it up in the normal table, right? Coming up with, ideally what you want to do is find the shaded area in the tail, right? And the shaded area in the tail here, unfortunately, didn't come directly from the p-table or from the z-table. We got the white area, not the shaded area, right? The shaded area here is 0.0869. Okay, 8.69%. Now, if you did this, you have just calculated, you took your z-test statistic, you went out onto the z-table, you found the shaded area that is that strange or stranger, and you came up with 0.0869 or 8.69%. Now what the p method asks you to do is to compare this number with alpha, or alpha divided by 2. Well, when you use alpha divided by 2, you deal with a two-tailed test. Why? Because in a two-tailed test, you would have 2 rejection regions. At a 5%, this would be 2.5% in that tail and 2.5% in this tail, right? What you are asking in the p method, right, is we want to compare how often we would get a result this strange, okay, in our standard normal. And that would happen 8.7% of the time. Now, if our 2.5% were here, if this shaded area is 8.7% and our alpha divided by 2, if we had a two-tail, but let's go back to the one-tail. And one-tail was 5. Right? This shaded area here is 5% of the time. You found out that from your z-test statistic, this shaded area to the right is more than alpha, and therefore, because your p-value is more than alpha, you reject the null hypothesis. If your p-value is less than alpha, you accept the null hypothesis. So what you end up doing is instead of doing it my way and saying 1.36, does that fit on this side? What it has you do is actually look up the area that is that strange. And that gives you the p-value. The p-value is the probability that you would have gotten a result z test this strange, this far away from the null hypothesis by pure luck. And if that probability is more than your alpha, you say, I will accept the null hypothesis. If it is less than alpha, you will reject the null hypothesis. Okay? So, bottom line is, you are most likely going to need to go to the z table regardless. Right? My method, it's much easier because you can do both the z and t, and it's much easier because you guys have learned how to cheat. And even when you're supposed to go to the z table, you go to the t table anyways, right? And go to the bottom line to get the z value, right? To get that z cutoff value, my methodology works perfectly fine, right? Here, you're going to have to go to that z table to figure out what that result is, right? Or you're going to have to go to the t table, and the t table is not going to help you because it's not set up that way. Now, some of you have statistics calculators, okay? My guess is that 90% of you who do have a statistics calculator and 90% of the people who have a statistics calculator honestly don't know how to use it. Right? Now, theoretically, it could give you the t-value that your table in the back of the book can't give you, right? Which would give you the shaded area further in the tail than the result you got. Right? Recapping, you get the p-value, you compare the p-value with the alpha value. If the p-value of looking this up in the z-table is larger than alpha, you accept the null hypothesis. You do not have a strange enough event to reject it. Right? Now, we said you compare this to alpha. Well, half the time you do that, half the time compare it to alpha over 2. Why? Because of half of the time you are dealing with a two-tailed test. Up until now, when you calculate the p-value is going to be the same regardless of whether you have a one-tailed or a two-tailed test. You just, at the very last, have to compare it to alpha or alpha divided by 2. Those are two different numbers. Which one do you compare it to? Well, if it's a one-tailed test, well, let's go to the two-tailed test. If it's a two-tailed test, right? If it's a two-tailed test, you compare it to alpha divided by 2. Why? Because in a two-tailed test, the rejection region, that alpha is split into two different sides. In the case of one-tailed test, you compare it to alpha. Unless you made the last mistake, right? The p-value will give you a probability of being this strange or stranger. Let us assume that our one-tailed test had the rejection region in this area. Right? And you did your p-value. Your p-value here is nothing other than looking at this value and looking up the z-test in the normal formula, right? And it gave you 8.69 or any number. Now, you want to compare this to alpha? And the answer is no, actually you don't. Why? Because this side of the tail is on the other side. It is on the acceptance side, right? There is no shaded area on this side. So anytime that you get a result that is on this side, and you calculate what the probability of getting a result this strange or stranger on the right-hand side, it's in the acceptance region. You don't compare it with alpha at all. You immediately say, oh, I don't even have to do this because the rejection region is supposed to be on the negative side, and the p-value of getting a result this strange or stranger is from a result that is on the right-hand side. And therefore, it's in the acceptance region automatically. So using the p method doesn't really save you very many steps because you still have to go look it up in the z-table, right? And when you are done, you have to compare it to one of three different things, which makes you need to think. And it would have been really, really nice if you had drawn the diagrams, right? Because without drawing the diagrams, you're going to make mistakes. And those three numbers you're comparing your p-value to are either alpha, alpha over 2, or you're comparing it to nothing because it's an automatic accept the null hypothesis, right? Not necessarily easy, right? So, net result, why bother? And my answer to that is, guys, don't bother. Be reasonable, do it my way. Because if you do it the p method, you're going to get to this point, and that last little thing, you're going to screw it up. Chances are 1/3 you get it right. Maybe a little bit better if you know what you're doing. If you are a pro at this, you'll do it really, really great. Okay. So, bottom line is, I am explaining the p method because at some point in time, somebody working for you is going to do a hypothesis test, and they're going to explain their result because they use the p method, right? When you look at their results, right, check to make sure, did they compare it to alpha over 2 or alpha? Did that make sense? Look at their results. Their results. Do they make sense just verbally reading it on a one-tailed test? Okay. Because if it's a two-tailed test, they got to be comparing it to alpha over 2. If they are comparing it to alpha, that means a one-tailed test, and you got to double check to make sure, okay, are you sure that they were looking at the right tail? Because doing this blindly will give you a p-value. It'll give you a p-value even when it is obvious you should accept it. All right? So the reason I'm teaching this to you is because we get people who learn how to do this in stats classes, and they will present it to you. Okay? Now, I am probably out of time. No, I'm not. 2:36. I will explain one more method. Okay, I gave you all the bad parts, right? Here's the good part. This is the part why some people who know what they're doing, professional statisticians, will use the p method. Because they will go and they will say, okay, let's go back to what we had before here. We could put the rejection region back on the other side. They will do this, and they will come up with that the p method equals 0.869 or 8.69%. And what they will correctly say is, boss, what? Because this is larger than alpha, we reject the null hypothesis at 5%, right? At an alpha equal 5%, we reject the null hypothesis. And all of a sudden, your boss says the following sentence to you. Okay, you're rejecting it out at alpha equals 5. Would you reject it at alpha equals 1%? In my method, you would have to say, wait a minute, I will have to redraw the diagram to find the new cutoff value for 1%. Right? In the P method, you wouldn't have to tell your boss, wait a minute, since you changed what alpha is, well, I can tell immediately 8.69 is more than 1%. So at a 1% level, it is still in the acceptance region. Right? If your boss then says, well, okay, so it is in the acceptance region if alpha is 5%, and it's in the acceptance region and alpha equals 1%, just hypothetically, would we be accepting this if alpha equaled 10%? If alpha equaled 10%, you would look and say, wait a minute, P is less than 10%, and so we reject the null hypothesis. So one of the big positives is if you have a boss who constantly changes his mind as to what alpha he's looking for, right? The P method doesn't make you redraw everything every time your boss changes his mind in terms of the alpha. Now, honestly, if your boss is doing that, your boss is looking for excuses to get the answer he wants, right? He's not looking for truth, right? He's looking to have somebody kiss his butt and not embarrass him and accept his null hypothesis, right? In which case you ask the question, okay, why in the hell did you have me do this to begin with if you knew damn well you weren't going to accept the answers, right? Most bosses would already know the alpha, but in this method, you don't need to know the alpha until the very last minute. Okay, that's one of the advantages of using the P method. The second you will see on Monday. By the way, we will have class on Monday, regardless of the fact that you guys have a test, because I need to get through not hypothesis testing, regression analysis. Okay, regression analysis is not going to be on the test. This P method isn't going to be on the test either. Okay, please don't use it on the test. If you use it on the test, don't expect me to be at all generous with partial credit. Okay? Do it my method, chances are you're not going to get it wrong. And if you do get it wrong, it's probably because of an arithmetic mistake that I take off a half a point or so. Right? So even if you get it wrong, you use the P method and you get it wrong, I am not going back and spending an awful lot of time trying to figure out, well, theoretically, what could he done wrong? Right? All right. Be reasonable. Do it my way, right? Which is not the P method. But the second reason why you should know about the P method is when we look at the computer output of regression analysis. And regression analysis is complicated enough that you will likely do it by computer. And one of the things that you will get as outputs, okay, is some P values, right? And that is, the P value is the probability of getting something this strange or stranger, if indeed there was no relationship, right? So, because that P value is calculated on the output of it, I needed you to see
Okay, how do you sort of use that p-value to make some kind of hypothesis tests? And the hypothesis would be the comparing the null value that there is no relationship, that the relationship is zero, right? Okay. And because it's on the computer output, I want you to be able to read the computer output, and I wanted you to hear my explanation about how the P method is calculated. Okay, remember the P method still needs you to do the test statistic. It's just once you do the test statistic, instead of seeing where it was on the graph you drew with the cutoff values, it says now that you got this Z test statistic, look this one up in the table and it will give you the probability of getting a result this strange or stranger, this strange or further in the tail of what you of the distribution. All right, any questions on that? You sort of see how in the P method there are multiple places that if you don't do this every day for a living, you're going to screw yourself up by accident. And that's why you be reasonable. Do it my way, step by step by step by step. It may take you a total of 2 minutes more, but you're going to be sure you got the right answer. All right. Any comments, questions? All right. Now, I put out on Blackboard the answers to your last test. Okay. A couple of you have emailed me and said, can you send me what I got wrong on the previous test? And I scanned it in your test and mailed it to you. For most of you, you can kind of look to see what the right answers were, and you should be able to figure out what you did wrong. Each number was worth 10 points. So when the number you got was divided by 70, which gives you the percent that is on your Blackboard number. Okay. If you want more details, email me. I'd be more than happy to scan it in and email it to you. Unless you want it, I'm not going to scan it in because not that it's a lot of work, but whenever you do something for 30 people, it's 30 times as much work as. So if there's 5 or 10 of you who say, yeah, send it to me, that's fine. That's easy to do. Let's take yours, take it to my printer, scan it in, email it to you. No problem. I'm not trying to hide it from you, but honestly, I think the number of people who actually look at, well, the result, most of you guys care what the final result was. And again, like I promised last time, on the confidence interval and the hypothesis test, those are the 2 tests that historically have the highest value of all tests. And the next one on Monday is going to be very, very similar in nature to what we did in confidence intervals, except instead of confidence intervals, they're going to be hypothesis test questions. All right. Any other questions? No? All right. Have a great weekend, and we will see you on Monday. Again, I'm going to have class on Monday, and I will open up the test probably a little bit earlier, probably at noon time, and then you will have 24 to 36 hours to complete it and mail it back to me, or to do it on the computer, right? You guys have gotten relatively good at it. I don't think there's a single one of you who sent me stuff on an Apple format for that. I am extremely grateful. Please do the same thing next time around, right? Okay. I can't read Apple's file formats or Apple pictures, but whatever method you guys used for this last test, go ahead and do it this way as well. All right. Take care. Have a great weekend. Bye-bye.